In this video, we're going to discuss eigenvalues and eigenvectors. In the last chapter, we saw that any linear transformation on a finite dimensional vector space can be thought of in terms of multiplying that vector by a matrix A. However, matrix multiplication tends to be a pretty intensive calculation because it involves a bunch of dot products of rows by the column vector, and each individual dot product involves n different multiplications by the various entries. And so what we want to do is to look for ways to make this calculation faster. In this section, we're going to introduce eigenvalues and eigenvectors, where we look for specific vectors in which transforming by a matrix A is the same as performing a scalar multiplication. So doing the scalar multiplication will be faster because it involves fewer individual multiplications. Okay, so here we have the definition of eigenvalues and eigenvectors. Right, so specifically an eigenvector is a vector such that when you do the multiplication A times X is the same as scalar multiplication of lambda times X. So this is the Greek letter lambda. And so this equation basically says that transforming by the matrix A is the same as scalar multiplication by the scalar lambda. So not every vector has this property, so we want to find the specific vectors that satisfy this condition here. So there might be, for a given matrix, there might be different eigenvectors where the scalar multiplication is by a different scalar. So we want to find all the vectors that satisfy this equation, and for each eigenvector, determine the associated eigenvalue. So for example, here we have a 3 by 3 matrix A, and you're given 3 vectors x1, x2, and x3. The claim is that each of these 3 vectors are eigenvectors. Right, so you can notice that they're different vectors, and not only that, the 3 vectors are linearly independent from each other. So we want to verify that these 3 vectors are actually eigenvectors, and in the process determine the corresponding eigenvalue that goes with the vector. Okay, so basically to verify that these are eigenvectors, what we want to do is we want to calculate A times X and get the result of that and see if the result is a multiple of the original vector. And so that multiple will give us the eigenvalue. Okay, so let's do the calculations one by one, right? So let's start with x1. So we calculate A times x1. So I'll write down my matrix A. X1 is this vector, 1, 2, negative 1. And we just carry out the matrix multiplication. So what do we get? So negative 2 plus 4 is 2, and then plus 3 is 5. 2 plus 2 plus 6 is 10. Negative 1 minus 4 is negative 5 plus 0, so you get negative 5. Okay, so this is the result of the matrix multiplication, and now I need to compare the resulting vector with the original vector and see if it's a multiple. Right, so you can see that every entry is a multiple of 5. Right, so this resulting vector is 5 times the original vector 1, 2, minus 1. And so this multiple here is the eigenvalue for this eigenvector. Right, so x1 is the eigenvector and 5 is the associated eigenvalue. So let's call it lambda 1 is equal to 5. Okay, so the first one is indeed an eigenvector. And so now we perform the same calculation for x2 and x3 and try to find the eigenvalue. So A times x2, A is still the same matrix, so we copy it down here. X2 is the vector negative 2, 1, 0. And now we carry out the matrix multiplication. So this is 4 plus 2, 6 plus 0 is 6. Negative 4 plus 1 is negative 3 plus 0. So you get negative 3. 2 minus 2 is 0 plus 0 is 0. So this is the result. Now I compare to the original vector, and you can see that each entry is minus 3 times the original. So this also checks out, and the eigenvalue here is negative 3. For eigenvector x2. Okay, so finally we verify the third vector. X3 was 3, 0, 1. So what is the result here? So negative 6 plus 0 minus 3 is negative 9. 6 plus 0 is 6. Minus 6 is 0. Negative 3 plus 0 is negative 3. So comparing, we see that this is a multiple of negative 3. Okay, so this is also an eigenvector, and the eigenvalue here is also negative 3. Okay, so we've determined that each of these three vectors are eigenvectors, and we've calculated their associated eigenvalues. Okay, so let's discuss how to find eigenvalues and eigenvectors for a matrix A. So let's look back first at the eigenvector equation. right? So ax equals lambda x. So let's rewrite this equation, right? So I can write x as the identity matrix times x, right? Because the identity matrix doesn't change a vector. And then let's rewrite the equation by switching the left side with the right side to get this equation. And now I'm going to subtract ax over to the left side. And so the right side becomes the 0 vector. And since x, the vector x, appears at the right end of both terms here, I can factor it out. But if you remember, matrix multiplication is not commutative. So when you factor something out, it should be factored on the same side it appears in, right? So when I factor the x out, it's factored onto the right side. Okay, so I get this equation here where lambda I minus a, this calculates to a single matrix, times x equals 0. So what this means is that for x to be an eigenvector, it has to satisfy this equation, which means that x belongs to the null space of this matrix, right? Because the null space is just all solutions to something times x equals 0. Okay, so so if we have an eigenvector, the null space contains other vectors than the 0 vector, right? Because from the definition, the eigenvector cannot be the 0 vector, right? So an eigenvector is non-zero. And so the null space is bigger than the 0 subspace. And so that means that this matrix here is not 1-to-1, and so it's not invertible. And it's not invertible so that the determinant of this thing is equal to 0. And so basically this discussion here will tell us how to find the eigenvalues in eigenvectors. Right, so an eigenvalue A is a scalar lambda, which satisfies this equation. Determinant of lambda I minus a is equal to 0. And the eigenvectors of A corresponding to a particular lambda belong to this null space. Okay, so one word about how the matrix lambda I minus a is set up, right? So minus a just takes the opposite sign of every entry in A, and lambda I is just a diagonal matrix with lambda along the diagonal, along every entry in the diagonal, right? So basically lambda I minus a is lambda minus the diagonal entries along the diagonal, and then all the off diagonal entries is just the opposite sign. Okay, so this thing here, this determinant here, when you expand it out, is called the characteristic polynomial, and it always has degree n. And when you set the characteristic polynomial equal to 0, this is called the characteristic equation for A. So basically the procedure is going to be the following, right? So you first set up this determinant and expand the determinant by cofactor expansion, and then you might have to simplify things a little bit. Then you set it equal to 0, and you find all roots of the characteristic polynomial by factoring or using the quadratic equation, quadratic formula, or by looking at the graph and see where it crosses the x-axis, or some other method to find all the roots. Okay, so, and then the roots of the characteristic polynomial are going to be your eigenvalues. And in this situation where you have repeated roots, the number of times each root repeats is called the algebraic multiplicity. So if all the roots are different values, then they all have multiplicity 1. But if you have repeated roots, you might have multiplicity greater than 1. Okay, so once you find all the eigenvalues, then what you want to do is to take the matrix lambda I minus A and plug in each individual eigenvalue back into the matrix. Right? So you do it separately for each eigenvalue, because determining the eigenvectors, you have to determine it separately for each eigenvalue. So you plug the eigenvalue into this matrix, and we're looking for the null space. Right, so that means you augment the 0 vector to the matrix, and then we do the row reduced echelon form, and from there we can find a basis for the null space, and this will give us a set of linearly independent eigenvectors. So one thing that's good to remember is that so the determining of eigenvectors takes a number of steps, and it's easy to make a mistake in your calculations somewhere in the process. And so if you remember that when you do the row reduced echelon form for this null space here, it will always have at least one row of all zeros. And so if that's not the case, that means that there's a mistake in the calculation somewhere. Okay, so let's see how the procedure works in an example. So we start by looking at a 2x2 matrix. So for this matrix A, we're going to separate into 3 steps. So first, we're going to write down the characteristic equation. Then from the characteristic equation, we determine the eigenvalues. And finally, once we have the eigenvalues, for each eigenvalue, we will find the corresponding set of eigenvectors. Okay, so first the characteristic equation. Right, so that means we have to set up the determinant of lambda I minus A. So it'll be 2x2 determinant. So on the diagonal entries, it's lambda minus the diagonal entries, right? So lambda minus a negative 3 becomes lambda plus 3. And then here we have lambda minus 2. And then off of the diagonal, it's just the opposite, right? So the opposite of 10 is minus 10. Opposite of 5 is minus 5. Okay, so now we have to take the determinant, and it's a 2x2 matrix, so we just do AD minus BC. Right, so lambda plus 3, lambda minus 2, minus negative 10, times negative 5. Okay, so let's expand this out. So what is this? Foiling lambda squared plus 3 lambda minus 2 lambda is plus lambda minus 6, and then this becomes a minus 50. Okay, so this is equal to lambda squared plus lambda minus 56. And so we get a quadratic, right? So the size of the matrix tells you the degree of the polynomial, right? So we should have a second degree. And so luckily this is factorable, so we don't need to use the quadratic formula. So what does this factor as? So 8 times 7 gives us 56, and so we want plus 8 minus 7. So lambda plus 8, lambda minus 7. Okay, so this is the characteristic polynomial, and so to get the characteristic equation, we set it equal to 0. And okay, so now each factor will give us an eigenvalue, right? So lambda plus 8 equals 0. So that means lambda is minus 8. So let's call this lambda 1 minus 8. And lambda minus 7 equals 0 means lambda is equal to positive 7. So let's call it lambda 2. Okay, so we have our two eigenvalues, negative 8 and positive 7. Okay, so A was to get the characteristic equation, so this was part A, and then getting the eigenvalues is part B, right? So these are our two eigenvalues, and then now we go to part C, finding the eigenvectors, right? So we do it separately for each eigenvalue. So let's start with the first one, lambda 1 equals 8, negative 8. So what we want to do is to take the eigenvalue and plug it into this matrix here, the lambda I minus A matrix, right? So along the diagonal, negative 8 plus 3 is negative 5. 7 gets plugged into here. So 7 minus 2 is 5. And then the other entries stay the same. So this is minus 10, minus 5. Oh, I plugged the wrong number in, right? So let's go back. My eigenvalue is lambda 1 equals minus 8. So minus 8 plugged in here. My negative 8 plus 3 is negative 5. Negative 8. Yeah, I accidentally took the second eigen. So negative 8 minus 2 is minus 10. And then these two entries stay the same. So minus 10 minus 5. I augment the 0 vector because I'm trying to find the null space. Okay, and then now we do the row reduced echelon form. Right, so the reason that I caught the mistake before, right, because when we do the row reduced echelon form, I need to have a row of all zeros at the bottom, right? So the only way that's going to happen is if the second row is a multiple of the first row. Okay, so row reduced echelon form. So I can divide this by minus 5, right? So 1, 2, 0, and then the second row will cancel because it's just a multiple of the first row, so that becomes all zeros. Okay, so the leading one is the first entry here, so that means that x2 is free. So we parameterize x2, then row 1 says that x1 plus 2t is equal to 0. So that means x1 is equal to minus 2t. Okay, so now I can write out the null space, right? So x1 comma x2, what is that? It's minus 2t comma t, and I can factor out a t, right, because it appears in both entries. Okay, so this says that any multiple of the vector negative 2, 1 it gives us an eigenvector with eigenvalue -8. So in particular, I can just take t equals 1 to get a particular eigenvector. So when t equals 1, you just get -2, 1 as an eigenvector. But again, I could have just taken any multiple of this vector as an eigenvector. Okay, so we have an eigenvector for the first eigenvalue. So now we have to follow the same procedure for the second eigenvalue. So let's do that. So lambda 2 is equal to 7. So I have to take 7 and plug it into lambda here. 7 plus 3 is 10. 7 minus 2 is 5. And then the other entries stay the same, so -10, -5. And I augment the zeros to row reduced echelon form. So I can just divide everything by 10 on the first row. And then the second row will cancel because it's just a multiple of the first row. Okay, so leading entry is here. It's x1, x2. x2 is free. So x2, say, is equal to t. And then row 1 says that x1 minus t is equal to 0. So that means x1 is equal to t. So what is x1 comma x2? It's just t comma t. And again, both entries have a t, so I can factor out the t. Left with 1 comma 1. And again, if I set t equals 1, I get a particular eigenvector. Say 1 comma 1. So I could have taken any value for t, but in this case it's simplest to take t equals 1. Okay, so I have my eigenvector for lambda 1, and I have an eigenvector for lambda 2. So to make sure all our calculations are correct, I can check that they're eigenvectors by just doing the multiplication as we did in the first page, right? So let's quickly check that again, because I mean this requires a bit of calculation, right? And especially if your matrices get larger and larger, it's easy to make a calculation error. Okay, so let's check. I take my original matrix A, right? So -3, 10, 5, 2. Times a vector -2, 1. It should be a multiple of the original vector, right? So see that this is 6 plus 10 is 16. -10 plus 2 is -8. And this is -8 times the original vector. So that checks out. What about the second one? So -3, 10, 5, 2 times this eigenvector 1, 1. So what is this? -3 plus 10 is 7. 5 plus 2 is also 7. But this is just 7 times the original vector. So this also checks out. Okay, so we have 2 eigenvectors, and also the corresponding eigenvalue checks out, right? So -8 and 7. Okay, so in this example, we have a 3 by 3 matrix, and we're going to follow the same procedure again to find the eigenvalues and eigenvectors for this matrix. So when you're trying to get the characteristic polynomial by doing the determinant of lambda I minus a, and for larger matrices, if all of the entries are non-zero, it can be quite a pain to get the characteristic polynomial. But this one's not too bad, right? Because at least I have some zeros, which simplifies things a little bit. Okay, so let's set up the characteristic polynomial. So it's the determinant of lambda I minus a. Alright, so it's lambda minus the diagonal entries, so lambda minus 1 here, lambda minus 1 here, lambda minus a negative 2 becomes lambda plus 2, and then I take the opposite of the other entries, so this becomes a minus 4, this becomes a plus 2, positive 2, this is 0, this becomes a minus 1, and this is 0. Okay. So, so now I have to take the determinant of this, right? And again, my matrix has a few zeros, so it makes things a little bit easier. So let's expand by the first column. And so it's lambda minus 1 times the determinant of this submatrix and then minus 0. Okay, so this is already going to be all zeros, but anyway, then it's these 4 entries, and then plus negative 1. Okay, so plus negative 1 becomes minus 1. And then it's these 4 entries, these 4 entries. Okay, so this is all 0, so that cancels out, and then now I need to multiply this out, so we have lambda minus 1, AD minus BC. Well, this is a 0, right? So it's this times this. So let's just FOIL it out real quick, right? So lambda squared minus lambda plus 2 lambda is plus lambda, and minus 1 times 2 is minus 2. Now this was 0, and then now this one. So minus, this is 0, minus this times this. Okay, so this minus was from this, then there's another minus because you're subtracting this, but then minus minus becomes a plus 4, so that's 4 lambda minus 1. Okay, so okay, so I mean I can FOIL this out, but there's a slightly easier thing you can do, right? So there's this term and this term, and both terms have the factor lambda minus 1, right? So I can factor out the lambda minus 1, and what's left over is this minus this. And so lambda squared plus lambda minus 2 minus 4. Okay, so then it's lambda minus 1 times lambda squared plus lambda minus 2 minus 4 is minus 6. Right, so if I multiplied this out, I would have had a 3rd degree thing, and then that's going to be difficult to factor, right? So by doing this way, the most I get is the quadratic here, which is easy to factor, right? So if I take a plus 3 minus 2, then I get plus 3 times minus 2 gives me negative 6, and then plus 3 minus 2 gives me a plus 1. So this is lambda plus 3, lambda minus 2. Okay, so it's completely factored. I set it equal to 0, right? So that's my characteristic equation. And then now the individual eigenvalues, let's list them from the lowest to highest, right? So the first one will be -3, and then +1, and then +2. Okay, so I have my eigenvalues. So last step is to get the eigenvectors, and again we do it separately for each eigenvalue, right? So I have to do it for lambda 1 equals -3, and we do it for lambda 2 is equal to 1, and we do it for lambda 2, lambda 3, lambda 3 is equal to 2. Okay, so what do I have to do? I have to plug in each of the, so starting for eigenvalue -3, I have to plug it back into this matrix. So -3 minus 1 is -4, and this will be negative, so this is -4, and this is -1. The other entries stay the same, so 0, -4, 2. Make this so smaller so it fits onto the screen. So the other entries stay the same, 0, -4, 2, 0, -1, 0. They augment all zeros. And then here, the eigenvalue is 1. So I plug in 1. So this is 0, 0, 3. These stay the same. Augment all zeros. And finally this one I plug in eigenvalue 2. So 2 minus 1 is 1. And 2 plus 2 is 4. And the other entries stay the same. Okay, so now I have to do the row reduced echelon form. Okay, so row reducing these is a little bit less straightforward, right? So I've already calculated the row reduced echelon form previously. It should be this one for this one for this, and this one for this. Okay, so these are augmented. Right, okay, so what do we have? Those are the leading ones. So this column is free, right? So x3 is equal to t. And then, okay, so what's row 2? Row 2 says x2 minus 1/2 t is equal to 0. I don't have so much space here. So this row is x2 minus 1/2 t is equal to 0. So what does that say? x2 is equal to 1/2 t. And then first row says x1 plus x3, which is t, is equal to 0. So x1 is minus t. Okay, so I basically ran out of space, right? So what do I have? They all have t, right? So I can factor out the t. And so what's the coefficient here? Minus 1, 1/2, and then 1. So if you don't like fractions, you can just take t equals 2. And so when t equals 2, what do you get? Negative 2, comma 1, comma 1. Okay, so that's the eigenvector for the first eigenvalue. Okay, so let's continue. Leading one here, leading one here. So x2 is the free variable. x2 is t. And then this is pretty straightforward. This says x3 is 0. x1 is equal to 0. So what is this? This is 0 t 0, which is just t 0 1 0. When you factor out the t, and so t equals 1 means I get 0, comma 1, comma 0. Okay, so that's the second eigenvector for this eigenvalue. And then okay, so now I need to do this one. Right, so leading one here, leading one here. That means that x3 is free. So x3 is equal to t. And then I have x2 plus 2t is equal to 0. That means that x2 is minus 2t. And then first row, x1 minus 4 x3, which is t, equals 0. So x1 is equal to 4t. So they all have a t, so I can factor it out. What's left over is 4, negative 2, 1. And so if you take t equals 1, you get 4, negative 2, comma 1 as my eigenvector for lambda 3. Okay, so these are the eigenvectors. I run out of space, so I won't check that they're eigenvectors here, but you can check by multiplying by the original matrix A. On this page, we're going to talk a little bit about the behavior of eigenvalues and eigenvectors, so we can sort of pay attention to things to look for as we do the calculations. Right, so the first thing is that for each eigenvalue, the corresponding, when you're trying to locate the corresponding eigenvectors, they form a subspace called an eigenspace, right? So I mean, the eigenvectors themselves can't be 0, right? So to form the subspace, you have to include the 0 vector also. But you get an eigenspace, a subspace called the eigenspace, right? So if we look back at the previous example, right? So if you look at the procedure when we're looking for the eigenvectors, right? So there's always going to be at least one free variable when you're doing this null space, right? So you can see each of them, I mean, there's only one free variable for each of them, but in any case, there's always going to be at least one free vector, right? So that means you can introduce a parameter, and so the number of parameters would tell you the dimension, right? So here I have one parameter, right? So basically this means that for any multiple t, you can eigenvector. I mean, I chose t equals 2 here, but I could have chosen t equals 1, t equals 3, so any real number t, right? And so this forms a one-dimensional subspace. Similarly here, for any value of t, as t varies, this forms a one-dimensional subspace. And here, as t varies, this forms a one-dimensional subspace, right? So this is what's called the eigenspace for the particular. So this is the eigenspace for this eigenvalue, this is the eigenspace for this eigenvalue, and this is the eigenspace for this eigenvalue. So we have the corresponding eigenspace for each eigenvalue, and so there's some restriction on what the dimension of the eigenspace can be, right? So as I said, there's always going to be at least one free variable, right? So the dimension of the eigenspace is always going to be greater than or equal to 1. But also, the highest the dimension of a particular eigenspace can be is the multiplicity of the eigenvalue, right? So again, going back to the previous example, because all the eigenvalues are distinct here, that means that their multiplicities are all equal to 1, right? So that forces the dimension of each eigenspace here to be exactly 1 in each case. Okay, so you have this restriction on what the dimension of each eigenspace can be, and the dimension of the eigenspace itself is called the geometric multiplicity. So you're basically comparing the geometric multiplicity to the algebraic multiplicity. Okay, so again, if all eigenvalues are distinct, then all the algebraic multiplicities have to be 1, and then the only thing between 1 and 1 is the number 1, right? So that means the dimension of each eigenspace also has to be 1, which is what we saw in this example here. Okay, so those are the eigenspaces, and one situation, I mean, for large matrices, trying to find the characteristic polynomial and finding the eigenvalues and eigenvectors becomes a tedious process, right? So there's one situation where it's fairly straightforward, and that's when you have a triangular matrix, right? So when you have a triangular matrix, the eigenvalues have to be the entries on the main diagonal, right? So and basically it's because the determinant of a triangular matrix is just the product of the diagonal entries. So as an example, we look at a 3x3 example here, right? So here I've chosen an upper triangular matrix, but it doesn't matter if it's upper triangular or lower triangular, right? So say you have A, B, C along the diagonal. I mean, they don't all have to be different, they could be the same, but whatever the diagonal entries are, and then you can have anything above the diagonal, right? So if you set up this determinant, then it'll look like this. Well, then this is still upper triangular, right? So when you calculate the determinant of this thing, it's just this times this times this, and trying to solve the eigenvalues, now you just get back A, B, and C, which is exactly the same as the diagonal entries. So at least for triangular matrices, it's a simple matter of just reading off the diagonal entries to get the eigenvalues. But when it's not triangular, then basically you have to follow what we did previously, right? So I mean, in this one, at least there are some 0 entries, so that simplifies the calculation a little bit, but you can see that it's not triangular, right? Because I have a 1 here, so it's not upper triangular, and then it's also not lower triangular. So basically you have to do this calculation.